Acids, bases, and salts. There are several different ways we can classify substances as being acids, bases, or salts. We'll look at the Arrhenius theory first. And when we deal with the Arrhenius theory for acids, bases, and salts, they're stated as substances that conduct electricity when dissolved in water. In other words, acids, bases, and salts are considered to be electrolytes. That means that when they dissolve in water, they break up into ions and can conduct an electric current. And we define acids and bases and salts depending on what the ions are that are formed in the solution. Acids are substances that ionize in water to produce hydrogen ions as their positive ions. And hydrogen ions are also sometimes referred to as protons. Bases are substances that ionize in water and produce hydroxide as their negative ions. And salts are neither acids nor bases. So they're substances that produce something other than hydrogen as their positive ion and something other than hydroxide as their negative ion. So here are some examples of Arrhenius acids and bases. If we have HCl and we put it into water, it will break up into ions. The ions it breaks up into are hydrogen ions and chloride ions. And since the positive ion is a hydrogen ion or a proton, we're looking at an Arrhenius acid. If we take sodium hydroxide and put it into water, it will break up into ions. We'll have sodium ions and hydroxide ions in solution. Since the negative ion is a hydroxide ion, sodium hydroxide is classified as a base. Another way we can look at acids and bases is through what's called the Bronsted-Lowry theory. And this theory redefines the terms acids and bases, because now instead of just looking at what ions are produced when the substance dissolves in water, we're going to look at what happens during chemical reactions. Acids in chemical reactions are substances that donate protons or hydrogen ions during chemical reactions. And that's very similar to the Arrhenius definition that says that it's a substance that has hydrogen ions. Here, though, we're saying that it's a substance that donates that hydrogen ion. Bases are substances that accept hydrogen ions or accept protons during chemical reactions. So they don't necessarily have to have hydroxide in their formula. Here are some examples of Bronsted-Lowry bases, acids. Let's say we've got hydrogen chloride gas and we add it to water. It's going to produce an ion which we refer to as a hydronium ion and a chloride ion. So let's look a little bit more at what happens. The hydrogen chloride gas loses a proton and becomes chloride. Since it's donating a hydrogen ion in this reaction, it's referred to as our acid. And when we look at water, water becomes hydronium in this particular reaction. So the water is gaining a proton, and by the Bronsted-Lowry definition, water is acting like a base in this reaction. So here's another example. We've got ammonia gas added to water. We're going to produce an ammonium ion and hydroxide ions. So we've got ammonia becoming ammonium, and we've got water becoming hydroxide. So when we look at the ammonia, it's gaining a proton. And by definition, any substance that gains protons is considered to be a base. And that proton's coming from the water, so in this case, the water is donating a proton. So by our Bronsted-Lowry definition, the water is acting like an acid. So if we look at these two reactions, in the first one, water's acting like a base. In the second one, it's reacting as an acid. And we call those kinds of substances amphoteric substances. Substances that can act like an acid and can act like a base, depending on what they're reacting with. Now let's look at the products. The conjugate base is the particle that remains after a proton has been released by the acid. So in this case, our hydrogen chloride gas is the acid. After it gives off its hydrogen, the chloride is our conjugate base. And if we look at water, water is accepting that proton. It's forming a hydronium ion. And a conjugate acid is the substance that's formed when a base acquires a proton. So when water accepts a proton and produces a hydronium ion, our hydronium ion is now our conjugate acid. So if we look at our second example, our ammonia is becoming ammonium, so our base becomes the conjugate acid, and I'm just going to put Ca there for conjugate acid. And water is becoming hydroxide, so this would be our conjugate base. Now these are reversible reactions, so if we were to look at the first reaction in the reverse direction, now the hydronium is becoming water. It's donating a proton, so it's acting like an acid. And our chloride is becoming hydrogen chloride gas. It's accepting a proton, so it's acting like a base. Let's talk about the strength of acids. When we look at acids, and we'll just say generically HA for an acid because it's got a proton that it can donate and it's got some negative ion, which we'll just designate as an A because it's an anion. And we add it to water, that acid is going to give up its proton to water and produce hydronium ion and whatever that anion is. Strong acids are acids that completely react, which means that the forward reaction predominates. A weak acid is an acid that only slightly ionizes in water, and that means that the reverse reaction is dominant. Now another thing we refer to when we talk about acids is how many protons there are to donate. A monoprotic acid is an acid that only has one acidic proton to donate during a chemical reaction. Hydrochloric acid is considered a monoprotic acid because it only has one hydrogen ion. Polyprotic acids, poly meaning many, are acids that have more than one acidic proton to donate during chemical reactions. And if we have polyprotic acids, the dissociation of that proton during the chemical reaction takes place one proton at a time. So let's use sulfuric acid as an example. Sulfuric acid is a polyprotic acid. We could actually call it a diprotic acid because it's got two acidic protons in it. Now each of those protons or hydrogen ions are going to come off one at a time. So in our first step, the first hydrogen is donated and we're left with a hydrogen sulfate ion. But since hydrogen sulfate also has acidic characteristics, we're going to have a second step where that second hydrogen ion is going to be given off and we'll be left with sulfate, which is not an acid. So acids can be characterized as strong or weak depending on the percent of the acid that actually dissociates in an aqueous solution. And they can also be classified as monoprotic or polyprotic depending on how many protons they have to donate during chemical reactions.